So this is section 4.3, problem number 25. And I'm going to analyze the graph of this rational function. I'm going to follow the steps. So the first step is to factor the numerator and the denominator of r and find the domain of the rational function. Well, I'm going to factor my numerator and denominator. First step number 1. So I have x squared minus 3x minus 4 over x plus 2. And I'm going to factor my numerator. And that looks to me like it would be x, and I'm going to have a negative 4 and a positive 1. All over x plus 2. So now I need to find the domain of this rational function based on having factored this. And the domain means the acceptable x values. So my biggest concern is I want to make sure I don't have a 0 in my denominator. Well, if x cannot be equal to negative 2, because if x is equal to negative 2, I will have a 0 in my denominator. So my domain is all real numbers except negative 2. And if I want to write that in interval notation, I would go negative infinity up to negative 2. A parenthesis, since negative 2 is not included, I put a union, negative 2 on to infinity. So that is my domain of this problem. I'm just going to go over here to my graph, which I'm going to keep track of as I go along. And I'm going to put domain x cannot equal negative 2. Write r in lowest terms. Well, I'm looking at my factor, so that's the number 2 here. My factored polynomial, my rational function, x minus 4, x plus 1 over x plus 2. And there's nothing that I can cross out for my numerator and denominator. So this is in lowest terms. If I could cross one of the factors off from my numerator and my denominator, then I would have to do that, and that would put it in the lowest terms. Step number 3. Locate the intercepts of the graph. That means my x-intercepts and my y-intercepts. Well, I like to start with my y-intercepts, because those are the easy ones. Y-intercept is where x is equal to 0. So let's plug 0 into my rational function here. I would have 0 minus 4 divided by 0 plus 1 over 0 plus 2. Well, that gives me negative 4 times positive 1 over 2. So I should have a y-intercept at negative 2. That's what it's telling me here. So I have a y-intercept at negative 2. Let's go to my graph, and let's put it in there in red. Y-intercept at negative 2. And of course, you will only have one y-intercept because it's a function. Even though it's a rational function, it's still a function. So I've got my y-intercept. What about my x-intercept? My x-intercept is where y equals 0. So if I want to know, if I'm looking at my original function up here, this is the same thing as y. So I'm going to set my original function equal to 0. Let's see if I can't do this fancy here. I'm going to go copy, and I'm going to come down here, and I'm going to go paste, and there it is. There's my original function. Let's move it down just a tiny bit, and I'm going to set that equal to 0. Well, I'm going to do this a long way, and then you will see the shortcut. I want to get rid of my denominator of x plus 2. So I'm going to multiply this side by x plus 2 over 1. And I'm going to multiply this side by x plus 2 over 1. And of course, you don't need to have the over 1, but it might help you a little bit. So my x plus 2's cross off there. So I'm left with x squared minus 3x minus 4 is equal to what? It's equal to 0. And you will notice, when I'm trying to find my x-intercepts, what I'm trying to find is where does my numerator equal 0? I'm not really concerned about my denominator. I'm concerned as to where does my numerator equal 0. So if my numerator equals, I've already factored this, my numerator, so I know that my numerator is equal to x minus 4, x plus 1, and I set that equal to 0. So that's telling me I have x-intercepts at 4 and negative 1. Okay, x-intercepts at 4 and negative 1. Let's go to my graph. Put those in. X-intercepts at 4 and at negative 1. Let's just write these down here. My y-int is at 0, negative 2, and my x-int at negative 1 and 4. Making some progress. Okay, so I found my intercepts. Test for symmetry. Okay? Symmetry, that's step 4. Well, even means that f of x is equal to f of negative x. And odd means that negative f of x is equal to f of negative x. So why don't I first find out what f of negative x is? So I'm going to paste my function back in here. Here's my function. This is f of x. So this is f of x. So f of negative x is equal to negative x squared minus 3 times negative x minus 4 over negative x plus 2. Let's see if we can simplify that a little bit. That's f of negative x. F of negative x is equal to x squared plus 3x minus 4 over negative x plus 2. Is this equal to this? No. So it is not even. Well, let's now see about my negative f of x. Negative f of x is equal to negative, and then I put in parentheses my whole function, right? X squared minus 3x minus 4 over x plus 2. And remember, when I'm making a negative of a fraction, I'm either going to make either the numerator negative or the denominator negative. I'm not going to make both of them negative. So let's make my numerator negative. Why not? We'll see what it looks like. I get negative x squared plus 3x plus 4 over x plus 2 is negative f of x equal to f of negative x? No, they are not equal. So no, not odd. So it is neither even nor odd. Step number 5. Locate the vertical asymptotes. 5. Vertical asymptotes. Well, the key to the vertical asymptotes goes all the way back up here to our domain. Our domain is x cannot equal -2. Wherever I have a domain exclusion, I am either going to have a vertical asymptote or a hole. So I'm going to write that down here. Domain exclusion will be either vertical asymptote or a hole. In this case, I have a domain exclusion of, so how do I know whether it's going to be a vertical asymptote or a hole? I'm going to pause here, and I'm going to take a detour. I'm going to write an equation here, a rational function, that is not the one we're dealing with. I'm going to write x plus 3, x minus 4, divided by x plus 3, x minus 2. It's a different rational function. But I want to point out how this works. My domain exclusion, domain x cannot be equal to -3, and it cannot be equal to +2. Those are these right here. -3, +2. Those are my domain exclusions. But if I put this rational function into lowest terms, it means I'm going to cross off the x plus 3's. And on my lowest terms, it will be x minus 4 over x minus 2. The part in the denominator that I crossed off, the part that gets crossed off, that is where there will be a hole. So this will be a hole, and this will be a vertical asymptote. So going back to my function that I am dealing with, let's kind of make a little squiggle line here so we know this was a different problem, just as an example. Going back to my original problem here, my lowest terms was the same as my original function. I wasn't able to cross anything off. So this exclusion from my domain right here, x equals -2, is going to be a vertical asymptote. So at -2, I'm going to have a vertical asymptote. So I'm going to go back here, and I'm going to say at -2, and I'm going to draw this in as a dotted line, a vertical asymptote. And this is what you are going to do on your quiz. -2. That is a vertical asymptote at -2. So I can put that vert asymptote x equals -2. I am going to continue on here with step number 6, locating the horizontal or oblique asymptote. So let's look at my function again. Here's my rational function. And this rational function, my highest power on my numerator is x squared, and my highest power on my denominator is x. So this is improper. In fact, this is really improper. I have a heavier weight above a lighter weight. If it was just improper, they would be the same weight. But this is really improper. So really improper means I'm going to have an oblique asymptote. And when I have an oblique asymptote, the way I find it is by doing polynomial long division. So if I'm going to do polynomial long division, I'm going to go x plus 2, and I'm going to divide it into x squared minus 3x minus 4. Oops. So what value times x is going to give me x squared? Well, I think that's going to be x, and I'll put that right above my 3x. So x times x is going to give me x squared, and then x times 2 is going to give me plus 2x. And now I'm going to subtract. I'm going to subtract 2x from negative 3x. That gives me negative 5x. Minus 4, I bring down my 4. And now I need to know what number times x is going to give me negative 5x. Well, that would be negative 5. Negative 5 times x is negative 5x. Negative 5 times 2 is negative 10. So I have here 4 minus 10 minus negative 10 is positive 6, but the remainder doesn't really matter. It would be plus 6 over x plus 2. This piece here doesn't really matter. This piece is what matters. That quotient right there is the equation of my oblique asymptote. So my oblique asymptote is y equals x minus 5. Let's go put that on our graph. Sorry, I made a mistake here and I'm erasing my mistake. Back there is a 4, negative 1, that's good. Okay, finish up, redraw in there. My oblique asymptote, so oblique asymptote y equals x minus 5. Well, don't forget, it's just a linear equation in the form of y equals mx plus b. So, our, I'm going to draw this in blue, our b, our y-intercept of our horizontal asymptote is negative 5. And we have a slope of 1, so that means over 1, up 1. Over 1, up 1, over 1, up 1. It's very nicely giving me a nice straight line. So this is my oblique asymptote. I'm just going to kind of sketch it in. There's my oblique asymptote. And I have to identify the equation. So the next question says, as part of step number 6, is I need to determine where, if any place, my function crosses my oblique asymptote. Well, if I had two functions, two linear functions, this is a different question. I'm going to separate this off right now. But if I had the equation y equals 2x plus 3 and y equals 4x plus 5, and I wanted to know where they intersected, I would set them equal to one another. So I would go 2x plus 3 equals 4x plus 5. Let's subtract 2x from both sides here, and I get 3 is equal to 2x plus 5. I subtract 5 from this side and that side. I get negative 2 equals 2x. I would get x is equal to negative 1. Again, this is not the problem that we're working on, but what this is telling me is that where x is equal to negative 1 is where the graphs of these two functions would intersect. So I can follow the same concept with my rational function. I have this is my rational function there. That's the equation of my rational function. And the equation of my oblique asymptote is x minus 5. I set them equal to one another to see where they might intersect. So let's multiply both sides of this by x plus 2. X plus 2. That gets rid of my denominator. So I have x squared minus 3x minus 4 is equal to, I can kind of FOIL this out. I'm going to get x squared minus 3x minus 10. And I can see pretty quickly here, well, I have x squared on both sides. If I subtract them from both sides, that would go away. I have negative 3x on both sides. That would go away. And I'm left with negative 4 is equal to negative 10. And that's, technical term, is nonsense. And since it's nonsense, it means no intersection with oblique asymptote. The next step in the problem is to graph it using my calculator. So I put the equation in, y equals, and notice you got to use your parentheses correctly. So I put my numerator in parentheses and I put my denominator in parentheses. And if I go zoom 6, this is the graph that I get. Well, I see a couple of things that are pretty good. I can see that I have my y-intercept of negative 2 is accurate. I can see that I have an x-intercepts at negative 1 and 4, just as I predicted. I'm not sure that this is my whole graph, though. I mean, I have to know that it is not the whole graph. There's another little piece of it. So what I'm going to do is I want to kind of step back and look at this a little bit more broadly. So I'm going to change my window. I'm going to make it negative 20 and positive 20, and I'll make it a scale of 2. And I'm going to make my y minimum, I'm going to go negative 30, and I'll make it positive 30, and I'll make it a scale of 3. Let's see what that looks like. Well, now you can see both pieces of my graph. And the other thing I'm going to do is I'm going to go y equals, and I'm going to put in a second equation. I'm going to put in the equation x minus 5, which is the equation of my oblique asymptote. And I'm going to go graph, and you can see that my oblique asymptote, it just kind of drew the line for me right there, and I can see that in fact it is an oblique asymptote. And so if I was to go back to my graph that I've been working on, it looks kind of like this. And I would just kind of sketch this in, and I might have to expand it on my graph paper, but really what I'm interested in you doing is just something like this, just that I know that you saw that it worked okay, that all your intercepts were good. If it happened to cross an oblique asymptote or a horizontal asymptote, you might mark in that point, but that's kind of what I am looking for on the, that's what I want you to be able to do, just like that.